Okay, thank you, thank you. So, okay, so where are the participants? Okay, participants are there. Download. Sorry, download. Yeah. Actually, now the recording has started. Okay, very good. Thank you for pointing this out. Mm, okay. Now, see. So we have been discussing about digital comparator. It's a logic circuit used to compare the magnitudes of two numbers expressed in binary. For the simplest case of comparing two one-bit numbers, so we have seen this is the truth table, and these are the input side. We have got only two operands, each of them being a one-bit variable, and on the output side we have got three functions, each of which is a function of two variables. And these are how we can fill up the conditions. And note that these are examples of completely specified Boolean functions. That means for no input combinations, the output value is unspecified. It is simply either logic 0 or logic 1. Nowhere it is X. That means unspecified. Now for this, however, we can get, suppose we are asked to implement this 1-bit comparator using only 2-bit NAND gates, 2-input NAND gates, then we require these we seen earlier. That means A exclusive or B, the minimum number of 2-input NAND gates required is 4, and then we just invert it one more time to get the equality. Here we get the A greater than B, here we get the A less than B. So 7 2-input NAND gates will suffice. However, suppose now we are asked to compare two multi-bit numbers. Okay, say we show it for 4-bit comparator, and we can expand it easily by means of the cascading inputs or expanding inputs. So expandability or cascadability should be ensured for whatever design we undertake to do in the domain of digital electronics. Okay, so 4-bit comparator, you see, first of all, it proceeds in a lexicographic manner. What do we mean by that? So lexicographic means you are looking for the meaning of some words in your dictionary. So how we do that? We start from the least significant one. That means, say, I want to find out the meaning of the word, say, bird, B-I-R-D. So to start with, it will tell me all the words, that the meanings of all the semantics of all the words which start with the word A. Say airplane, alligator, everything and everything. So after the A part is finished, that means the first letter A, we exhaust the list, then we start with the name B. Okay, and again after B is the leftmost letter, after that I comes. So BAT, bat, then B ND, bend, after that then I will come. Okay, so then BI, then again BI, after that R will come. Okay, so that means first of all say bin, BIN, then what else, say BI R, before R you have got say BIPAP, BIPAP, then BIR will come, then after BIR D will come, something like that. So lexicographic means that we have to start with the leftmost end. Here for comparison what we do, we start from the least significant end. So that means if we want to compare, say 1010 and 0110, 8 and 6. So our comparison will start from the least significant end. Okay, so just visualize that. One, what we have been saying, say 1 followed by 3 zeros. That denotes the decimal value 8, and 0 that denotes the decimal value 6. So our comparison will start from the A0 and B0. Here we find that they are equal. Then we go over to the next higher end. So that means 0, 1. Okay. So for 8 you have got 0, for 6 you have got 1. So now we can say, well, temporarily we make it that 6 is greater than 8 because 1 is there. Fine. Then after that again 1 will come. So now we see that as if B is less, greater than A. But finally, for the most significant, in this case we are limited to 4-bit numbers, we find that A3 is greater than B3. Irrespective of whether, you see that for, if you take the first number as 8, so A3 equal to 1, A2 equal to 0, A1 equal to 0, A0 equal to 0. And for 6, B3 equal to 0, B1 equal to 1, B2 equal to 1, and B0 equal to 0. So comparing A0 and B0, we find they are two equal. Then we go over to the next higher order. Okay, so where we find that A1 is 0, but B1 is 1. So B1 is greater than A1. Again, we find B2 is greater than A2. But when you go over to the most significant case here, the A3 and B3, we find that A3 is greater than B3. So now we make a decision that as in the order of significance, okay, A3 and B3 has the highest order of all the remaining bits. Then as A3 is greater than B, we conclude that the number A is greater than B. Okay, 1000. Now we extend it. Suppose we go from 4 bit to 8 bit. How we do that? Now we discuss. So this is called the lexicographic way of comparing two multi-bit numbers. Now,
Excuse me, sir.
Yes, yes.
Sir,
Yes.
why are we starting with the least significant bit? Because if we start with the most significant bit, wouldn't it be easier to see which number is greater than the other?
Yeah, exactly. That is also possible. Exactly. And you will find that I don't know, actually, normally when we used to hold the class in classroom using Blackboard, so we did it either way, from least significant n as well as most significant n. Fine, there is no problem in that. Okay, I mean, you will be surprised that, well, if we do it thoroughly, it will be clear. The meaning is that suppose we do it after we write the equation, it will be clear. Exactly, you are right. So starting from the most significant n means the comparison will be less. Okay. And if we start from the least significant, the comparison will be a bit more. But overall, we find that the complexity of the electronic circuitry that is required is more or less same. I'll show you. So here, for example, first of all, before we take up the comparison of two 4-bit numbers, let me define first. This is also well known, the equivalence or equality. Equality means when we can say that two bits are equal to, means they are equal in magnitude. Either both of them are at logic 1 or both of them are at logic 0. So it is simply writing, this is the equivalence function, that means with a big circle, and within that you embed a dot. So this stands for the equivalence function, okay, 2-bit equivalence function or equality comparison. So AI equals BI. If you expand it out, it will be AI and with BI, then OR with this, and product is OR with AI dot BI. Okay, so equality of 2 bits is guaranteed if this function is 1. Now consider two 4-bit numbers A3, A2, A1, A0, B3, B2, B1, B0. Okay, so cascading inputs and outputs, why are they required? Because suppose we are designing a 4-bit comparison, we can expand it to say 6-bit or 8-bit, 10-bit, 12-bit, however, whatever way you want. Okay, so we have to just repeat that we have designed a 4-bit comparator and we have stored the design, we have frozen the design, that means having designed it, implemented it, validated it, testing it thoroughly, and find that, okay, there is no errors creeping into the design, okay, or into the hardware. So fine, if we are satisfied, then we store the design in our, what you call, the library. Library means that it's a database. So there the design is stored, frozen, and then we can, when you have to go to 8-bit, we just copy it. That means just repeat the design. Okay. Now, so this is the structure. For your benefit, I show one block diagram. Okay, so this is the block diagram of a 4-bit comparator, and you see that what are the required inputs, what are the outputs. Outputs, as before, you see that regardless of the fact whether the two words involved between them, say only 4 bits or say 1024 bits, okay, the number of outputs remains the same. That means only 3 outputs will be there. One is that we are taking two multi-bit operands and we are symbolizing them as say A and B. Then we wish to know at the end whether A exceeds B, A is greater than B, or A equals B, or A less than B. No further output is required. So regardless of the word length of the two operands, the number of outputs will remain same, namely only 3. Okay. Now look at the total number of operands for a 4-bit comparator. When we are undertaking the task that we have to compare two 4-bit numbers between them, then as the 4 bits from each of the word will be taken into account as the input. So 4 plus 4, 8, plus 3 cascading inputs are there. Now what is the need of these cascading inputs? So they are a way of communicating from the less significant stage, whether in the less significant stage, that means we have started from the least significant end, let us say. Okay. So that means whether as we are progressing to higher order stage, whether in the less significant stage, the two other means two, I mean not two, not four, but it can be say, suppose we are now comparing between say bit, suppose we have so far we have seen up from B0 to B7, A0 to A7. Now here instead of comparing say x3, x2, A10, the higher significant, that means say x8, x9, x10, x11. Okay, that means the third nibble from the last 10, from the least significant. So whether x9, x10, x8, x9, x10, x11 and y8, y9, y10, y11. Okay, having compared the two lowermost nibbles, and the result of comparing the lowermost two nibbles will be conveyed through these three cascading inputs. So there, if this is 0, if this is 1, suppose I have put it 0, 1, 0. Why I have put it 0, 1, 0? That I also explain. Now, suppose what is the meaning of A less than B in? It means that so far, that means we have started our comparison from the lowermost end. We have seen so far that A and B are two numbers which we are comparing. So for example, we are in the say first nibble means A0 to A3, B0 to B3. Okay, then second significant nibble means A4 to A7, B4 to B7. Okay, and now suppose on this particular 4-bit operands, I have inputted say x8, x9, x10, x11, here y8, y9, y10, y11. Good. So that means what will be conveyed through these three cascading inputs? It will be conveyed that the result of comparing the least significant 8 bits of number A, that means starting from A3 to A7, and that for the number B, that means B0 to B7. That means we understand here, if A7 to A0, this 8 bit, whether it is lower in magnitude compared to B7 to B0. If this is 1, I mean, you also get to know that three cascading inputs, okay, having done some comparison already, now they will be mutually exclusive. That means one and only one of them will be 1. Okay, so that means if we have found that A7 to A0, they are less than B7 to B0, these 8-bit numbers, then this will be 1. Okay, the topmost input will be 1, namely A less than B. And this IN stands for, the subscript IN stands for input. This out stands for the subscript out. Okay. So we understand if this input is 1 and we are at the moment comparing the, what you call the first nibble means A3 to A0, B3 to B0. Second nibble means A7 to B4, B7 to B4. And third nibble means the A11 to A8, B11 to B8, right? So suppose in place of X3, X0 and Y3, Y0, I have put X11, X10, X9, X8, here Y11, Y10, Y9, Y. So if we get here 1, 0, 0, it means that the result of comparing A7 to A0 and B7 to B0, these two 8-bit numbers, I find that the relative magnitude of A7 to A0 is less than B7 to B0. Okay. And suppose I find that this is 0, this is 1, this is 0. Now it means that the result of comparing A7 to A0 and B7 to B0, these two 8-bit numbers, is that two of them are equal. Okay. And lastly, A greater than B means that the result of comparing A7 to A0 and B7 to B0 is that the 8-bit number A7 to A0 is greater than B7 to B0 in magnitude. Clear? Read out. And so now I believe what we do, we stage-wise convey this information, that the result of comparing the lowermost significant part of the two numbers, if A is less than B, that means the part that is relevant for A and the part that is relevant for the number B. We are comparing A and B, two multi-bit numbers. Suppose A is a 32-bit number, B is a 32-bit number. Then if we can manage to design a 4-bit comparator without any error, then we have to just repeat the design for this 4-bit comparator 8 times. Okay, so means 8 nibbles will be there for a 32-bit number, all of you are sure. Nibble means it is a combination of 4 bits. Okay, so when you are comparing A0 to A31, B0 to B31, these two 32-bit numbers, we simply require 8 number of this 4-bit digital comparator. Clear? Okay. Any doubt here? Okay, if not, let me explain how these three output functions are dependent on. So each of them, can I ask you one thing? So these three output functions are there. Now each of these output functions is a Boolean variable, is a Boolean function of how many variables? See, these three output functions are there. This we have to design. We have to logically specify and then think of the gates. Gate design is not of much significance because you know that what gates you require. My question is that these three variables, a less than b, a equals b, and a greater than b, and the subscript out means that they stands for output function. Now each of them is a function of how many variables? Who can answer? Tanoy, are you there? Or who else? Kushal?
So 9.
Yes, sir.
Yes, sir.
That means each of the each of the three output functions is a function of how many variables? How many? Answer. You look at the block diagram. You should be able to tell me. Why are you so delayed?
So 9.
Why 9? 7.
8.
See that? There are 4 inputs corresponding to 4 bits corresponding to the word A. 4 bits corresponding to word B, and only these 3 remaining cascading inputs. So 4 plus 4 plus, I'm sorry, 11. I'm sorry, it's a function of 11 variables, right? Again, please concentrate. A0, T3, these are 4. See, within the block, see, when you are drawing a block, something remains invariant. What are they? These 3 identifier or designator for the output function. These 4 for the part of the operand A, these 4 for the part of the operand B, and these 3 for the cascading input. So this A0, A1, A2, A3, B0, B1, B2, B3, and these 3 more. So 4 plus 3, 11. These are the inputs, and each of them stands for the output. So each of the output functions is a function of no less than 11 number of variables. Clear? Here also, these two.
Sir?
Yes, yes.
Sir,
Please ask me. Yeah.
Sir,
Sir,
the output A equals to B out depends only on A equals to B in and the 4-bit nibble, right?
yeah, I mean, yeah, let me explain. So these, yeah, one by one I'll explain. So that is what I mean to say is that these 3 functions, anyway, it may be don't care on the some of the variables, but overall you can see that. So what you have to do, you can 11 means 2 to the power 11 input combinations can be there, right? Okay, 2 to the power 11 combinations means 2048 combinations can be there. 1024 means 2 to the power 10. So I have to do for all 24. Means if I am very thorough, if I am very formal, then I have to find out what are the possible output values for each of the 2 to the power 11 or 2048 input combinations. But I'll be somewhat intelligent that not all of them will matter. However, that means if we want to find when this becomes equal, then I have to look for only whether this is 1 or 0 and what is the bitwise comparison of say between A0, B0, A1, B1, A2, B2 and A3, right? So that means will be involved when trying to specify the say middle one, that means A equals B, then it matters only whether this is 1 and if this is 1, in addition whether the comparison of A0 and B0 will give me 1, that means whether this is true. That means E0 means what? E0 means basically ending of A0 and B0 or with A0 bar and B0 bar. Okay. So E0 basically if you expand it out, it means that the AND A0 B0 with A0 bar B0 bar. E1 means it relates to A1 and B1. So that means A1 ANDed with B1 or with A1 bar ANDed with B1 bar. Again, E2 means what? The equality, the bitwise equality. E2 means that whether A2 equals B2, that means A2 ANDed with B2 or with A2 bar ANDed with B2 bar. Finally, E3 means A3 and B3 or with A3 bar ANDed with B3 bar, right? So that means this I am writing E3, E2, E1, E0 symbolically, but E2, E1, E0 are nowhere involved here. If you expand it out, E0 means we will be forced to what is E0 that is related in terms of A0 and B0. So that means you see here the 8 inputs are getting involved, right? That means E3, E2, E1, E0, if we expand it out, flatten it, then we are forced to involve all these 8 variables, namely A0, A3, A2, A1, A0, B2, B2. And then in addition, this one cascading input. Now, what is the role of this? The A less than B on this, we can say, regardless of their presence, okay, it is we are not concerned with this output. That means this is output is independent of A less than B, A greater than B. That means when we want to find the condition when this particular function takes up the value 1, it is compulsory, it is imperative that this function, however, this variable should, however, have the value 1. In addition, bitwise comparison between these two. That means overall, I can say this is influenced by how many variables? 9. Because this, if you flatten this out, E0, E1, E2, E3, I get to know about the magnitudes of A0, B0, A1, B1, A2, B2, A3. All these 8. In addition, this one cascading input. So 9 variables will influence the value of this function. Clear? Okay. So in overall, you can see that whatever be the value of this, okay, so it will not influence this, right? And similarly, when we want to find out when A is less than B, that means what is the result of comparing, that means the result of comparison of the lower significant part of the two operands will be conveyed by the cascading inputs. Okay, so here we can surely say that having compared up to say 12 bit, that means up to A0 to A11, B0 to B11. So as we know about the comparison of A0 to A7, B0 to B7 at these 3 inputs, so if this comes to be, now you say A less than B, if this becomes 1, I know that the result of comparing A7 to A0 and B7 to B0, this 8-bit component on the lowest significant end, now A is less than B, then only this becomes 1. Okay. So if this is 1, in addition, the result of comparing these 4 bits are what you call equal, then we can say that, well, up to comparing A0 to A11, okay, the 11-bit number is corresponding to A is less than the 11-bit number corresponding to B. Okay. I mean, these conditions are all mutually exclusive. Okay. That means, you see that if the equality holds and in addition these holds, then I can say A is less than B. Or else, suppose the equality does not, suppose this is not true, then I have to look for this. And here you can at once find that of these 4-bit numbers, these two are the most significant. So if A3 happens to be less than B, we can at once say, well, the 11-bit corresponding to number A is less than the 11-bit corresponding to B. Now, if it so happens, then, well, these two are equal, A3 and B3 are equal. Then I have to once again check for the just lower significant A2, B2. Here, if it is so that E3 is 1, that means A3 and B3 are equal. In addition, if A2 is 0 and B2 is 1, then what happens? Then I can say, well, as this is the A3 and B3 are the most significant, okay? A2 and A2 is just the lower significance. So if the most significant bits are equal between them, then and A2 is less than B2, then I can say, well, this operand A is less than B. And gradually we are proceeding towards the lower significant end. So actually you can say if these two bits and these two bits are equal to themselves, then what about A1, B1? If here I find that A3 equals B3, A2 equals B2, but A1 is less than B1, then I can at once conclude then, well, what A so far as regards the comparison up to 12 bit is less than B. Otherwise, what can happen? Suppose the equality holds good over A3, B3, A2, B2, and A1 even. Lastly, you just pay attention to A0 and B0. Here I find if A0 is less than B, so that means this is the way we argue in English verbally. We put it mathematically like this. If E3 and with E2 and E1 and A0 bar and with B0, then it will be, we can at once make a conclusion that word A is less than word B. So that means we have to look for 5 distinct conditions. Okay, 5 distinct conditions, and the conditions overall, I mean, in totality, they will be mutually exclusive. That means if this holds good, suppose the first condition holds good, then the other 4 are false. What do you mean by the first condition holding good? Is that so far this is 1, in addition bitwise equality. Okay, so for that I have got this logical way of putting the condition. The second condition is that very crisp. They only say whether A3 is less than B3 or not. If I find that holds good, then immediately I can say, well, now regardless of the other conditions, of course they cannot be hold good all at a time. So if this holds good, then the entire number is, the entire word A is less than B. Or else if the third condition is true, when the third condition is true, when these A3 and B3 are bitwise equal, in addition A2 is less than B2. That means A2 is 0, B2 is 0, B2 is 1. That holds good when E3 and with A2 bar and if B3 that is true. So then I can say that word A is less than B. Else, if equality holds good over the most significant 2 bits, namely A3 equals B3 and A2 equals B2, in addition A1 equals 0, B1 equals 1, then I say that, well, as a whole, word A is less than B. Finally, look at this condition. What it states that if A3 bitwise is equal to B3, A2 is equal to B2, A1 equal to B2, and A0 is 0, B0 is 1. Okay, that means E3, E2, E1, A0 bar, B0 is 1. Then also I can say what is what equal to less than 1. Clear? And A, when to infer that whether A is greater than B or not. For that, again, similar 5 conditions. Okay, so these are the conditions. I mean, it is just like the previous output, only the less than, here the less than symbol gets replaced by A greater than B. That means instead of this cascading input becoming true, now only this cascading input becomes true. And the other conditions you see that exactly same as before. Not exactly same. Actually, here A3 bar B3, in place of that A3 B3 bar. I'm sorry. That means here, if I have to find out whether the word A overall is greater than word B, if this condition holds good, fine. Otherwise, I have to check whether A3 is greater than B3. That means if A3 is 1 and B3 is 0, that means A3 B3 bar. Okay. If it is true, I can immediately say, well, the word A is greater than word B. Or else, if A3 equals B3 and A2 is logic 1, whether B2, where else, A2 is at logic 1, I mean at the same time B2 is logic 0, then also we can say that word A is greater than 1. And similarly this and similarly this. Okay. So that means this is regarding the comparison of 4 bits at a time. In addition, what is the situation regarding the comparison of the lower significance? Clear? Now, to put it more concrete, suppose we want to find out, say 2 numbers are there, we call them X and Y. Okay, we call them X and Y. Then the result of comparing the lowest significant nibble, namely X3, X2, X1, X0 and Y3, Y2, Y1, Y0. We call it to be a lower nibble comparator. That means the comparison now is carried out over the lowest 4 bits. Then see, this is the lowest end. Now the result of comparing the lowest nibbles of word A and word B is propagated to that comparator which compares the immediately higher significant nibbles. Okay, and likewise suppose the 2 8-bit numbers. So problem is that consider two 8-bit numbers, namely x dealing with x, this is 8-bit number, y dealing with x, y 7. So how many comparators are required? Suppose you are designing a 4-bit or nibble comparator using these three equations, these three Boolean equations. So what are the gates required? You can easily find that I require an exclusive NOR gate. Okay, how many exclusive NOR gates to input? Or equivalence gates? I require 4. Then they are ANDed. So I require a 5-bit AND gate. Okay, 5 input AND gate and 4 number of 2 input exclusive NOR gates. Okay, and here how many I require? I require you see a 5 input OR gate and say here 5 input NAND gate. Okay, all this, and also that 4 number of 2 input equivalence gate are common to all these three, right? So overall, if you are asked to draw the gate diagram, draw the 4 number of 2 input exclusive NOR gates only once. Why only once? Because their output can be fanned out to the inputs of the further subset. And for TTL, you just tacitly assume that any gate has a fan-in of nominally 10 value, right? So no problem with that. So only generate E3, E2, E1, E0 only once, and then use them multiple number of times. There, is it clear? Okay. So this design takes care of the lowest significant 4 bits. Here, however, you have to consciously put the 3 cascading input values. Okay. So for the least significant stage, this has to be forced to the ground, the lowest one also forced to ground, and force it to go to logic 1. Here they should be decisively connected to some what you call constant values. Constant value is either say logic 1, let me say 5 volt or 3.3 volt and 0 for ground. After that, it is simply an interconnection. Okay, that means that just interconnect, make a connection between the A less than B output of the one comparator and with the A less than B input of its immediate right neighbor. After that, there is no other what you call forcing of the constant value. After that, it is simply interconnection. So these are also known as the interconnection signal or cascading signal. Interconnection means just between two modules, we convey some information. Here, the values of these are clearly determined by the output values of this immediate left neighbor. Immediate left neighbor means that is of lower significance, and immediate right neighbor means that is of immediately higher significance. Okay, so for comparing two 8-bit numbers, you see that having designed this, I just require 2 of them and no other gates. Mind you, no other external gates. Only I just design this circuitry, digital circuitry, put them in a box, repeat them. Repeat them is just in a factory assembly line. Once you have put the components in place, now it will be a simple repetition of the overall module. Okay, so that means no other external gates are required. So that is the beauty of drawing the significance right from the lowest significant levels. Now, as a home task, what you do? Please take this home task. Suppose you get the information from the uppermost level. Then what? How much? Sorry. What will you require? Get it? That means, see, all of you, have you followed it? What I want to say is that if you design thoroughly a 4-bit digital comparator, and suppose once you are designing two 4-bit numbers, next you need to design between two 8-bit numbers, you just require 2 modules, nothing else. Dear friends, nothing else you require, no other external gates. Suppose 12-bit numbers, how many modules you require? 3 modules. 16-bit numbers, only 4 modules. But no other external gates. Let me put it forcefully. No other external gates will be required. Now, if you apply I suggest that you take a home task. towards the evening, we just think of the problem. Well, now the communication will be from the upper nibble comparator to lower nibble comparator. All of you, can you read it properly? I have written lower nibble comparator. Why do I say so? Why do I say so? And this, why do I say that this is upper nibble comparator? Anyone?
It operates on the lower bits and the other one operates on the higher
Very
bits.
good, very good. So that means the lower significant nibbles are compared here, the upper significant nibbles are compared here, and the information regarding the comparison of lower nibble is propagated to the immediately higher upper nibble comparator. Now I want to make a tweak in the problem. I say that, okay, dear students, give me one comparator, but now the communication will be from upper nibble side to lower nibble side. So just slight change will be there in the design equation, nothing much. But what I wish to means I ask you to think over it, that whether you require external gates or not. Okay, and you will find that the design will not be this regular. Regular means what? See, you see that regardless of whether I am comparing to 8-bit numbers or 12-bit or 16-bit, the overall connection will remain the same. That means only at the least significant end, you need to put it directly to ground, the middle one directly to logic 1, and the lowest cascading input directly to ground. And then whatever is there inside, that is common for both. That means the internal construction of the two blocks or multiple number of blocks are identical, no change. That means if you blindly put you see that I am writing A3, A2, A1, A0, B3, similarly here also. What I put it from the outside, that will be the actual values. But internally, this gate configuration remains absolutely identical, no change. Okay, so after that, what I require, just interconnect by a wire from this output to this in, from this output to this input, this output to this input. No other change. Again, if you want to compare between the higher nibble, just from here to the input, here from the input, but no other change. Now, if you want to solve the problem in other way, that means solve from the highest end first. Then whether you require some extra wire, you will find that you will definitely need, you will definitely require some extra wire. That means final decision about the comparison of two 8-bit numbers here will be from the rightmost end. Similarly, if you employ 3 modules, the final decision whether the two 12-bit numbers are less than or equal to or greater than, that will be from the rightmost end. Similarly, if you are comparing two 12-bit numbers using, however, trying to propagate the result from upper nibble to lower nibble side, you see that there will be some irregularity, some lack of regularity in the design. That I wish you to thoroughly look into that. Okay, tomorrow you'll tell me the answer, whether it will be as simple as that. Simple means it is a perfectly regular connection. Only here you need to put the values to the constant Boolean values. Otherwise, it's simple, same actually. Just connect from here to here, here to 3 wires. Again from here to here, 3 wires. Okay, and other wires are remaining same. Okay, so no other external gates will require.
Sir, for the home task, won't the internal implementation of the blocks be different? Like
Yeah,
these will not be.
yeah. You just write the equation, nothing else. Means how many gates will you, that will be now a easy task for you. That is a cakewalk. That means how to implement that you all know, because I require here 4 number of twin input equivalence gates or 4 number of twin input exclusive NOR gates. Then connect it with this. So I require a 5 input AND gate. That is known to all of you. Here also I require a 5 input NAND gate. Here I require a 2 input AND gate, 3 input AND gate. Okay, 4 input AND gate, 5 input AND gate, finally a 5 input OR gate. Internal gate
Also, sir,
diagram.
can we use external gates, or do we just need to use these blocks?
Exactly. That means having written the having written what you call the uh, Boolean expression thoroughly in terms of, see, you will require these 4 and these 3. That means this digital comparator block diagram, it will remain the same. Only the output equations will vary a bit, and also I ask you to ponder about the fact that probably you require some irregularity. Irregularity means what? From the uppermost nibble, some extra wire will need to be taken out. From the next layer, some extra wire need to be taken out. Like here you told, here I can surely point out that apart from these wires, these interconnections, no other external gates are required. But when you are comparing from the upper side and conveying, that means here just interchange their position. Put the upper nibble comparator here, lower nibble comparator, and so on. That means you start from the leftmost comparator will correspond to comparison of the uppermost nibble comparator, and then gradually you are going to less and less significant stage. Okay, and take the output from the final rightmost end. Here on the other hand, what we are doing, we are comparing for the least significant end. That means the lowermost nibble comparator, you compare first, put their information to the immediately higher nibble, and then going up and up the significance ladder. But I ask you to redo the design. You start from the topmost ladder in terms of significance. Then as you proceed towards right, you are going what you call increasingly lower and lower significance. Okay, here you are going in increasingly upper and what you call higher significance. Suppose you redo the design, start from the highest significant end, proceed. As you proceed, you are going down the ladder. That means progressively lower and lower significance. Then see whether the design remains as elegant. Why do I say this is elegant? Because see, just you repeat these blocks and just make sure these connections are there. And also at the leftmost end, this should be connected to ground, this should be connected to ground, this should be connected to ground. And then blindly you take the result from the rightmost end. Okay, now redo the design where you start from the uppermost nibble, gradually as you go towards the right, okay, you proceed towards the lower significant end. Finally, you take the output from the rightmost end, no doubt. But see whether some extra connections you require. If not get some extra connection, you may require. But you look into the problem. Tomorrow we'll do this. Okay. I think so far no problem is there. Nah? Any doubt still? Have you got what I want you to do?
Yes, sir.
Okay,
Sir, yeah. We have to make that reverse comparator using the same block which is shown here, or do we use a different block with different equations?
No, dear friend. The output equation will slightly vary.
See, yes, so the output equation will vary. So we have to change this block with external circuitry, or do we use the block as we we create a separate block for it?
Yeah, let me tell you the problem. You will require 4-bit this nibble comparator as before. That means these connections A3A2, A1, A0, these three and this. That means total 11 inputs and 3 output. They will be invariant, no change. Only the equations will now vary a bit. That you have to write. That means logical equations. That means overall, there will also be 11 inputs and 3 outputs as before. Only the output, the logical equations will change a bit. How that you think of, and so and then interconnections will be there still, no problem. Now what we will put here and what we will put at the right post in, that you just give a thought. Okay, that means you start from the highest significant end, carry out over to the gradually lower and lower significance. Finally, you reach the least significant end. Here, what you do is start from the least significant side. Gradually, you progress toward the higher and higher significant end, and in the final nibble, you have the comparison between the two highest significance. So, for example, here 8-bit number, you can experiment on the two 8-bit numbers also. That means here, what I have done, I require 2 nibble comparator between 2 8-bit numbers. Okay, these are lower nibble, these are upper nibble. Now, what do? I just reverse the connection. That means in place of lower nibble, I bring the upper nibble here and bring the lower nibble, and the information regarding the comparison of upper nibble is conveyed to the lower nibble comparator. Then how the equations will vary? And it will be a general equation, no doubt about that. But whether you can take the output from the rightmost end, this rightmost output, whether it will be as simple as before or somewhat less regular. Okay, tomorrow I'll discuss. Okay, no problem. Just so far you try to think up what will be the, how the what do you call, the block diagram will look like. Block diagram will be same, even a slight change can be there, and also the equations, nothing else. Okay, and just keep this in mind here. Please remember, all of you, that no other external gates are required and no other external wires also. Wherever you go, that means suppose I am comparing two 16-bit numbers. How many comparators are required? 4 number of them. No, wherever you focus, that means dynamically you put your attention here. You find that, well, I can see from the outside 4 wires enter, 4 wires enter, and these 3 wires from the left neighbor, 3 wires go to the right neighbor. Everywhere the same situation. Okay, here also 4 wires enter. From the left, 3 more wires are entering, and from the right end, 3 wires are going out to the immediate right neighbor, but no other external wires. Remember, this picture will remain the same everywhere. That means you are comparing to 20-bit numbers. I require 5 of them, right? Because each nibble compares between 4 bits, so I require 5. But everywhere I focus, I find that the same connections. Clear? And remember, that in every stage, I bring my focus here. I put my eye here. I find that on my left, I stand here. I find that on my left, the comparator is engaged in comparing with, say, some nibbles. Right? On my right, however, the comparators are there, but they are taking care of the immediately higher 4 bits. Everywhere they say. Similarly, when I ask you to solve the problem in another manner, here in place of lower nibble comparator, on my left will be the upper nibble comparator, on my right will be the lower nibble comparator. And then how the equations will change. Definitely they will change, as you can understand. Okay, because comparison between the information which is regarding the upper nibble comparison and using them here will be different than using the information regarding lower nibble comparator and using them here. That will slightly change. So definitely there will be slight change in the output equations. In addition, you see whether I can get the result directly from the wires which are coming out here, or something else will be required. That you, for your intelligence, I leave the problem to you. Okay. Now what I do is that, let me go over to the next problem. Still there is any doubt? I believe not so, no? Okay. Let me take up the next problem. This is regarding realizing a Boolean. I'm sorry, I missed it. There is a Boolean function. Realizing a Boolean function using a multiplexer tree. That means any Boolean function can be implemented by utilizing, by employing a tree of multiplexers. Tree means what? At each of the nodes of the tree, there will be a multiplexer of appropriate size. By multiplexer tree, a tree-like structure. Say, for example, here one figure have you. So this is the root of the node. So in the root node, in the root node there is a multiplexer 2 to 1 multiplexer, and in the other nodes, intermediate nodes also there are 2 to multiplexer, and there the leaf nodes also 2 to multiplexer. So everywhere in the tree, each node will be accommodating a multiplexer of proper size. Say here I am putting a 2 to 1 multiplexer. Instead of I could put a 4 to 1 multiplexer, 8 to 1 multiplexer. Clear? Normally I'll try to see that the order of the multiplexer is the power of 2. I can work with 2 to 1 multiplexer. That is the lowest significant, that is the least what do you call? Least complex one. Okay. Then 4 to 1 multiplexer, 8 to 1 or something like that. I will not work with a 5 to 1 multiplexer, 3 to 1. Theoretically we can do that, but to keep the matter simple, I'll go by the, say, 2 to the power n to 1 multiplexer. Now, number of levels of the tree. Here, how many levels? 1 level, 2 level, 3 level. The number of levels of the tree depends on the type of multiplexer. It means whether I am using 2 to 4, 4 to 1, 8 to 1, something like that. And the number of variables involved in the function. Two things are important. That means what is the nature of the multiplexer what is the complexity of the multiplexer, and finally how many total number of variables are involved, whether it is an 8 variable function or a 10 variable function, 12 variable or 4 variable or 5 variable like that. So this is a function. N can be any integer number, positive integer. It requires n levels, right? That means as many variables are there, those many levels. Levels means here 1, 2, 3, 3 levels. Mind you, all of you understand now what do you mean by the level? So you can call this to be level 1, level 2, level 3, something like that. So 3 levels. If I use only 2 to 1 multiplexer, I require as many variables are there, those many levels. So three variable function means 3 levels are required. Okay. If all 4 to 1 multiplexer, I require n by 2. So what is this function? Ceiling function, all you know? All of you are done programming and data structure. Ceiling function you know, is it not? Suppose n equal to 5. What will be the value of this ceiling? Anyone? Say 5 by 2, that is 2.5.
3.
It will be 3. Very good. Okay. So ceiling means, the way I write it here, it means the least significant integer which is greater than equal to n by 2. Okay. So if n equal to 4, then this ceiling equal to 2. But if n equal to say 4.1, then it will be 3. Okay. Or 4.2 or say 5. If n is 7, it will be 4. If n equal to 9, it will be 5. Clear? So those many levels are required. In general, if only 2 to the power m to 1 multiplexers are used, then I require n by m and ceiling of that. Let me clarify the problem. Suppose n is the total number of variables. Okay. Suppose I have to implement a 9 variable function. That means n equal to 9. And what is m? M is say 2 square to 1. That means 4 to 1. So n equal to 9, m equal to 2. Then how many levels are required? 9 by 2 equal to 4.5. I require 5. Now I make the multiplexers a bit more powerful. That means I make it say, well, 4 to 1. 4 to 1 means m equal to 2. So I require here n means 9. 9 by 2, I require 5. But suppose I make it more powerful, say it becomes 3. So n is 9, m equal to 3. That means 8 to 1 multiplexer, I require only 3 levels. That you can easily see by writing on your paper. For the simple one I do here in the class, all of you please pay attention. It is a very simple problem. Consider realizing a 3 variable function x3, and also remember that in order of significance, x3 has the highest significance, x1 has the least significance. Now I always try to impress on you that you always, whenever you are writing a function of some variables, please pay attention to the order of the variables. So if I write say variable a comma b comma c, here I've written x3 x2 x1. So the leftmost variable will always have the highest significance, and the rightmost variable will always have the least significance. Okay. So x3 x2 x1, when we write, that means x3 has the highest significance, x2 and x1. Now again you can question, what do you mean by significance? Yeah, significance means that if I draw a Carnot map, okay, I write say 0, 1, 2, 3, 4, 5, 6, 7, say 4 variable. So that the midterm index will be determined where x3 has the highest, means it comes first, followed by x2, followed by x1. Okay. Using only 2 to 1 multiplexer. Basically, the way this tree has to be drawn is based on Shannon expansion theorem. That means SOP form of the Shannon's expansion I can write. So this is the highest significant one. That means you take it out. Okay, if you write the complement of the variable x3 bar, then everywhere within the algebraic expression replace x3 by 0. That is one part. In the second part, okay, if x3 has been taken out, and everywhere within the function you replace the occurrence of x3 by logic 1. Clear? Again, this you expand. That means I expand this in this form, that x3 bar, and if 0 comma x2 comma x1, what I expand in the next level, that I write within the 2 box brackets, the third bracket. So here what I do, x2 is now in the next order of significance, x2 comes out, x2 bar, replace everywhere within that the occurrence of x2 by 0. Okay, then x1 remains in the variable form. now x3 and x2 have been replaced by some constant. Here also x2 has been taken out and replaced the sub-expression involving x2 and x1. Everywhere the occurrence of x2 is replaced by 1. Similarly, you expand this part. Okay, and then finally what you are out? What you do? You expand out x2, x1. Then finally what you will get? Nowhere x2, x1 or x3 will remain, but it will be replaced by either 0 or 1. So outside x3 bar, x2 bar will be there. Then what you do? This is the way. That means first time you take out x3, you get this is taken care of by these two these 2 to 1 multiplexer. So where x3 is connected to the controller select input of the 2 to 1 multiplexer, y is the output. At the output point, you get the final function, and at the two inputs, I0 will be propagated to the output when x3 takes up the value 0, and I1 will be propagated to the output y when the select function s takes the value 1, right? So here, when x3 is taking the value 0, then this coefficient will be present at this input, and when at the I1 will be taken out to the output when s equal to 1 or x equal to 1. So when x equal to 1, this is the coefficient. So this input, that means f1, x2, x1 will be taken at this input. Okay. Now again you are expanding this, so now you are in the second level. Okay, that means in the level 2. That means we are proceeding towards the leaf of the nodes, where finally the leaf nodes will consist of the constant values. Mind you, these are merely constants. If you expand it out, it will be either 0 or 1. Nowhere any variable is involved. Okay, that means at the leaf node, all the inputs are nothing but constants. Okay, so here you see that this corresponds to what? This bracketed term. So this corresponds to a single multiplexer, where x2 is coming to the input, select input, right? So that means here f0, x2, 1 will correspond to which one? This one. Okay, so x2 is taking the value 0, then f0, 0, x1 will come here, and f0, 1, x1 will be appearing here. Okay, and this part corresponds to this particular multiplexer. Oh, sorry, that means x2 is applied as the select input. If when x2 takes the value 0, then this coefficient should be propagated to the output. So that corresponds to 1, 0, x1. 1, 0, x1, what do we mean by that? That means x3 is replaced everywhere by 1, x2 is replaced everywhere by 0 within the algebraic expression. Okay, nothing else. Similarly, if 1, x1 means it corresponds to this input, which will be propagated into the output of this 2 to 1 multiplexer when x2 takes the value 1. Finally, if you replace these 4 coefficients, okay, by taking out the value x1, that means I require 4 more multiplexers. Say if 0, 0, x1 will be implemented by this 2 to 1 multiplexer. If 0, 1, x1 will be implemented by this multiplexer 2 to 1. And similarly, these two sub expressions will be implemented by these two multiplexers. So finally, I require 4 plus 2 plus 1, 7 multiplexer. Okay, in general, when you are employing say 2 to 1 multiplexer, I require 2 to the power n minus 1 multiplexer. Here n equal to 3. So 2 to the power n is 8, 8 minus 1, 7 multiplexer. Okay, and in each of the level, I require the number of multiplexers will be a power of 2. Here it is 2 to the power 0, 2 to the power 1, 2 to the power 2. That is a simple of that. So you have followed. I mean, any doubt? Okay, now see. I just have a real function. Okay, so real function means what? This is the majority function. Why do I call it a majority function? I believe it is clear. Okay, so it is a carry output function. I call it a majority function because say 3 variables are there. When majority number of variables takes up the value 1, then it takes up the value 1. Function will takes up the value 1. So considering 3 variables, the majority is 2. That means when 2 variables are taking up the value 1 or 3 variables are taking up the value 1, then the function value takes up the value 1. That's why it's called AB odd with BC odd with AC. It is called a 3 variable majority function. Now implement the function using a tree of only 2 to 1 multiplexers. Now let me tell you In straightforward or unoptimized design, you may require 7 multiplexers. But as an engineer, your task is always to reduce the cost. So reduce the number of multiplexers in the circuit if possible. Not all the functions it may be possible. But if it is possible, please go ahead. So you know that what are these 8 constant inputs corresponding to a 0, 0, 0. This is here 0. Then this is a 0, 0, 1, that is 0. So it is very clearly you can see that here it's a majority function is wherever 2 or more variables are taking up the value 1, so function value is 1. Okay, so that means here f0, 1, 1, here you see 1. This is m1, 0, 0, so only one variable is 1, function value is obviously not 1. And for the remaining 3, these are 1. So now, if you do like that, what I can do, I can rewrite the expression. Here you see that regardless of the value of select input, both inputs take up the value 0. So unbiasedly, you will get 0, always. Here, it depends on C. If C is 0, then 0 comes here. If C is 1, it comes here. So it will be C. Similarly, this one. And here also you find that, I have forgotten to write C here. So regardless of the value of C, 1 will come. So 0, C, C, 1. And now in the second stage, you see that now the input is x2. So in place of x2, I write B. So if B is low, then 0 will come here. If B is high, then C will come. So at this point, I get BC, the expression. And here similarly, if B is low, then I get C. B is high, I get 1. So how do I write? Why? This B bar and it with C or with B. And using absorption theorem, it will be B or with C. And finally, I verify that indeed I'll get the expression of FABC to be AB or with BC. Now here I wish that you have noted that as 0 will come here independent of the value C. So why put this multiplexer? You can remove the multiplexer. Similarly here, why to put this multiplexer? You can remove the multiplexer. No point. In fact, I find that here also I get only the variable C, only variable C and the 2 constant. So these 4 multiplexers are no longer required because this is the Boolean constant 0. This is the Boolean constant 1 and only the variable C. So why to keep those multiplexers? I don't require. First, fine. So I just put 0, C, C and 1. So what remains is that only these 3 multiplexers will remain. I can do away with these 4 multiplexers. So in the optimized circuit, I require only 3 2-to-1 multiplexers. In the straightforward unoptimized instance, I require how many? 7 multiplexers. Okay. So dear friends, I think now we have to stop now because you may have to take lunch and then take some rest and then start the lab class. Okay, so all of you have got it. Any doubt here? Dear friends, are you here?
Yes, sir. Yes.
Okay, so any doubt, just let me know. Tomorrow, again, we'll come at 10 o'clock. We'll start the class. So thank you for your attention. And if still any doubt, you can ask me, no problem. Regarding this 3-to-1 multiplexer, it's a very elegant way to realize any Boolean function straightforwardly. See, any Boolean function you can expand in SOP form or POS form also. SOP form is better if you want to realize using, if you want to look for a mechanism for implementing the function using multiplexer. In fact, multiplexer is called a universal logic module. Using multiplexers, you can realize any Boolean function. Okay, so you know that if you have got n number of variables, that the exhaustively how many Boolean functions are there? It is 2 to the power n. That means corresponding to 2 variables, the total number of functions will be 2 to the power n. That means 16 functions for 2 variables. Okay, and if you have got say 3 variables, x2, x2, what are the exhaustive number of functions that we can have? So that will be 2 to the power 3 or 2 to the power 8 or 64 functions we can have. That can be done by writing the truth table and replacing everywhere the function values by 0 or 1. Okay, so you can easily understand. So that means 2 to the power n input conditions will be there, and for each of the 2 to the power n condition, the function value can be either 0 or 1. So the exhaustive number of functions possible for n variables is 2 to the power n. That means if you have got only one variable, it will be 2 to the 1 or 4. Say x bar or 0 or 1. Right? Similarly, for two variables, there can be and or, NAND nor are anyway there, exclusive or exclusive or then there can be implied or implied. Okay, we'll discuss later. So that means the trying to realize a Boolean function using a multiplexer tree is a very important problem. Okay, and also how many levels you will require, that will depend on the complexity of the multiplexers as well as the total number of variables involved in the Boolean function. So here the example that we have taken in the class is a simple one, 3 variables and 2 to 1 multiplexer. Okay. So if you have say five variable function and you employ 4 to 1 multiplexer, then you require 3 levels, and you can try to write out the this Boolean constant, what you will require and what are the levels. Okay. Why? Because n equal to 5 and m equal to 2. So 5 by 2, 2.5, and ceiling function value will be 2.5. Its ceiling is the least significant integer that is greater than equal to 2.5. That is nothing but 3. So you require 3 levels and 4 to 1 multiplexer using, but nothing else. Nothing. And again, for certain functions, you will see that some of the multiplexers will be redundant. So for example, these 4 are immediately found to be redundant. I require only the 3 multiplexers. Why they are redundant? Because their output function is a 0 CC. Now, if it is even in place of C, if you have BC or A bar C, then also why to put a full multiplexer? Just use an AND gate BC. Yes, any doubt, any question, please? Yes.
Sorry to interject, sir.
No, please. Yeah, welcome, always welcome. Yes, yes. Yeah,
So
please.
we have a to so we have to have lunch before that.
Oh yes, sorry. Yeah, I'm sorry. I will not return. So tomorrow we'll meet at I think 10 o'clock. No, okay. Have a fine day. Please stay.
Thank you, sir.
Good health. Okay. So wishing all of you a very good health and please fantastic stay in your home. Okay. Any doubt, just let me know. Okay. Thank you very much. Thank you. Tomorrow we'll see. Okay. Thank you all of you. Okay.
Thank you, sir.
Thank you.